Hi, my name is Clemens Lutz, and today I'll present our work on the Triton join, efficiently scaling to large join state on GPUs with fast interconnects. I've conducted this work together with my colleagues Sebastian Bress, Steffen Zeuch, Tilman Rabel, and Volker Markl. The goal of our work is to scale GPU-accelerated joins to a large join state. We can have terabytes of data, which leads to large base relations, which we term R and S. Because the base relations are big, we like to accelerate the join using a GPU. We can transfer the base relations ad hoc across an interconnect to the GPU. However, we can only store several tens of gigabytes of data in the GPU's onboard memory. Thus, the join state can easily exceed the GPU memory capacity. Besides the memory capacity limitation, a premise of state-of-the-art joins is that the interconnect bandwidth is also limited. Specifically, PCI Express 4.0 has a bandwidth of only 24 gigabytes per second per direction. These two factors, the memory capacity and the interconnect bandwidth, lead to a well-known problem in the database community called the data transfer bottleneck. In contrast to these works, we're using a game-changing technology which we call a fast interconnect. Fast interconnects such as NVLink 2.0 provide much higher bandwidth at up to 65 gigabytes per second per direction, and we measure that NVLink is actually on par with the main memory bandwidth of the CPU, and it's 2.7 times faster than PCI Express 4. In addition to NVLink 2.0, several next-generation interconnects are becoming available soon, such as NVLink 4.0 from NVIDIA, Infinity Fabric from AMD, and the Compute Express Link from Intel. Next to these GPU technologies, there are also fast interconnects for FPGAs, like OpenCAPI from IBM and the cache-coherent interconnect for accelerators from ARM. The contributions that we make in this work are that we revisit GPU hash joins while considering a fast interconnect. We then identify the hardware bottlenecks that occur despite using a fast interconnect, which leads us to contribute an out-of-core radix-partitioning algorithm that's optimized for fast interconnects. And building on that, we propose a new Triton join algorithm. Our agenda for this presentation is to revisit GPU hash joins, and then we'll look at the Triton join algorithm. A typical approach for constructing GPU hash joins is to first read in the smaller relation R and use that to build a hash table in GPU memory. We then transfer the larger relation S to the GPU as well and use that to probe the hash table. Okay, so let's look at the performance of this approach. On the x-axis, we're scaling the build and probe relations up to a data size of 30 gigabytes joined with 30 gigabytes. On the y-axis, we're measuring the throughput in gigatuples per second, and we're looking at two devices, an IBM Power 9 CPU with 16 cores that's running an efficient radix join, and an NVIDIA V100 GPU with NVLink 2.0, which is running a no-partitioning join. What we can see is that the GPU achieves a speedup of greater than 2x over the CPU. However, the join state is limited by the GPU memory capacity. In contrast, the CPU continues to scale to a larger data size. Thus, the GPU hash join does not scale to a large join state. We can extend this approach to spill the hash table from GPU memory to main memory for large join states and access the hash table out of core via the interconnect. This means that the GPU also scales beyond the GPU memory capacity, but there's a performance cliff for very large hash tables. Thus, spilling the hash table does not lead to robust performance for the no-partitioning join. Taking a closer look, up till now we were using perfect hashing, which doesn't handle hash conflicts. If we replace perfect hashing with a linear probing hash table, which does handle hash conflicts, the hash table size then doubles. And what we can see then is that there are now two performance cliffs. One of those occurs because of the GPU memory capacity, like before, but it occurs sooner. But there's a second performance cliff that occurs when the hash table size exceeds the TLB range. The second drop looks small, but these TLB misses cause a 400x decrease in performance versus the perfect hashing variant. Thus, TLB misses cause a slowdown for large hash tables. There's a more sophisticated state-of-the-art join approach that we call the CPU partitioned radix join. This one takes the relations R and S and partitions them using the CPU in main memory. And then we can copy a partition from R and a partition from S to the GPU, because these partitions are now small enough to fit into the GPU memory. And then we can perform the join on these partitions using the GPU. This approach scales beyond the GPU memory capacity, and it's also robust and actually achieves a speedup of 1.5 times over a CPU, even for a large join state. But this CPU partitioned radix join requires a fast CPU and a fast GPU, and thus the CPU partition join is not resource efficient regarding hardware resources. To summarize the challenges, a higher interconnect bandwidth, and I want to emphasize that we're using a fast interconnect, is necessary but not sufficient to achieve a high scalability. In our work, we discover a key insight. Namely, we can stream the data from main memory via the interconnect to the GPU and use the GPU to partition the data, and then write back the partitioned data to main memory, also across the interconnect. Thus, fast interconnects enable us to create a fast out-of-core partitioning algorithm. Let's look at the performance of this partitioning approach. We're going to measure throughput in gigabytes per second on a data size of 15 gigabytes using a fan-out of 512 partitions. And what we see is that the GPU is 1.6 times faster than the CPU. And thus, a GPU with a fast interconnect outperforms the GPU even when everything is in main memory. Building on top of this insight, we propose our Triton join algorithm. The Triton join works as follows. We take the base relations R and S, and we do a first pass over the data with our new out-of-core radix partitioning algorithm using the GPU. That means we read in the base relations from main memory and write the partitioned data back to main memory. Then we perform a second partitioning pass also using the GPU, where we read in two partitions from main memory to the GPU, and this time store the second order partitions in GPU memory. After that, we read in these partitions and build and probe a hash table that we construct in the GPU scratchpad cache. And finally, we can emit the join results. In addition to the out-of-core radix partitioning, in the Triton join, we cache as many partitions as possible in GPU memory and only spill partitions to main memory when we run out of space on the GPU. That's why we don't actually need to read in all of the partitions from main memory for the second pass, and instead only those partitions that we couldn't cache. Thus, the Triton join is a new hierarchical hybrid hash join for the GPUs. Coming to our evaluation of the Triton join, we can see that the Triton join scales efficiently beyond the GPU memory capacity, and it does so while achieving a speedup of greater than 2 times over the CPU. Thus, the Triton join scales to a large join state. In comparison to the GPU no-partitioning join, we can see that the performance of the GPU degrades gracefully while scaling to a large join state. And when comparing the Triton join to a CPU partitioned radix join, we can see that the Triton join achieves a 1.3 times speed up over the CPU partitioned radix join. And this is despite the CPU partition join using a CPU and a GPU, whereas our Triton join uses mainly a GPU. In the Triton join, all what we're doing on the CPU is computing a prefix sum over the keys and some task scheduling. Thus, the Triton join efficiently processes joins end-to-end on the GPU. Overall, I'd like you to take home that our Triton join exploits fast interconnects to scale to a large join state, by robustly spilling states to main memory, and thus we're able to efficiently process the join using the GPU. With that, thank you for your attention, and I'm happy to answer your questions in the Q&A, and feel free to reach out to me via email anytime.